My name is Jeff Zemerick. I work for a company called Mountain Fog. I'm a consultant there, and the work that I'm talking about to today was done for a client recently. And so in this talk, we're going to see how we can use neural networks to do document classification to help improve documents going through a workflow. So we'll describe the workflow, the data that we have, how we create our document classifier, how we made auto-suggest with using learning to rank, and the tools that we used. So the background, as you might have guessed, is there is a workflow. And it doesn't look all too different from a giant traffic jam, actually. The documents in this workflow are highly technical documents. They are artifacts that were created, and I'll describe them a little bit later on, but they contain a lot of technical text, not really dictionary words. A full trip through the workflow can take some time to complete because there are humans involved during the workflow. When I was thinking about this work, I could not help but think of the Plinko game from The Price is Right, that I at least know and love, and hope everybody does too. So the Plinko game from The Price is Right is somewhat like a workflow. You instead of a document, you have a chip, and you drop your chip into the workflow, and it goes through some set of path until it gets to some cache value at the bottom. And at the bottom, you see there's zeros where you get nothing, so your trip through the workflow was not a good one. And then there's other values, and of course there's the 10,000 in the bottom center, and that's what everybody wants to get. You want to get that $10,000 on there. So when we play Plinko, you can almost overlay some type of random workflow on top of it. The only problem with Plinko is, unless you've mastered the game by some means, when you drop your chip at the top, it's largely random. I guess you could probably spend some time studying the right thing to do to get the 10,000. But it is mostly random. So unlike this workflow, our workflow is not random. There are things that we can do during our workflow to help us get the documents in the workflow to a most successful resolution, which in the case of Plinko would be the chip landing on the $10,000. So this is our document workflow. This is a very simplified version of the workflow, trimmed down to just the important parts, just the parts that matter. So a document starts in the new state. So that's whenever you go click File New, it's in the new state. In progress is while the document is being authored. So it stays in progress for as long as it takes the author to complete the document and submit it. Once submitted, it goes to a submitted state. In the submitted state, documents can sit there for a long time, sometimes days, sometimes weeks. It's really hard to tell. Based on the attributes of the document and some things, it could sit there for a little while. And so then there's three terminal states once it gets submitted. The document can be rejected, the document can be canceled, or the document can be approved. So you might have guessed, the approved state is the one that we're looking for. So that's our $10,000 Plinko slot. Rejected and canceled are not ideal states. They are the end of the workflow. But our goal here is to get as many documents as we can to the approved state. And so this work focuses on how can we help those document authors get their documents written in such a way to become approved. So about these documents, due to the nature of the client, I can't really say a whole lot about the document. But I can tell you that the documents are very technical in nature. They contain many non-dictionary terms. Some of them are mostly non-dictionary terms. Names like components and things like that. They're not very long documents typically. On average, usually around 500 characters in length. Some, of course, are much longer. Some, of course, are much shorter as well. Each document is written by a single author. We have many different authors throughout the whole system, so many different types of writing styles. But there is typically a one-to-one correlation between a document and an author. And like everywhere else, there's varying levels of author experience. Some of these authors may have just started employment. This might be their first document they've ever written. Others may have been there for 20 years. They're experts. They know what to write. So many different types of experience and background from the authors going into it. And the documents have associated metadata. It's essentially just key value pairs. And these key value pairs, we'll see later on that we can use those. But for now, it's just enough to know that there's metadata associated with each document. So the goal that we want to do is we want more documents to ultimately be approved. We want them to go through the workflow and exit the workflow in the approved final state. This means that they have a positive resolution. It's the ideal situation. It's also important to remember throughout this work and the presentation, of course, is that documents are not inherently good or bad, high quality or low quality. Just the documents have different attributes that we can try to exploit to try to help them get to a favorable outcome. And so we want to provide that feedback to the authors. So if we can do something that while an author is typing up a document, that we can give them feedback that will say, hey, your document is not looking like it has a real good chance here. You might want to change some things based on what we've seen before. So that's what we want to do. So our approach, 3-step approach that we have here. The first step is to use past documents to try to predict the final state for new documents. So we have a large collection of documents that have gone through the workflow and ended up in many states. So we have those documents. We will try to create a classifier from those documents to predict the final state for new documents. Step 2, provide tools for the authors to help improve their documents. So having some prediction about a new document is helpful, but it's not super helpful. Imagine telling an author there's a 0.1% chance your document is going to be improved. The author's going to say, oh, well, great, give me some help here. So we want to be able to give them feedback a little more helpful. The last step is to integrate it. The classifier and the tools are not very useful if they're not integrated into an existing system. So step 1, the document classification. So on our workflow, what we're after here are the red X, Y, and Z's in the workflow. We want to know those percentages that a document, the probability that a document will be rejected, canceled, or approved. And we want to take that percentage and we want to pass it back to the author while the document is in progress. So the training data that we have 3 sets of documents, and those 3 sets correlate to the 3 final states in our workflow. We have documents that are approved, have been approved. We have documents that were canceled and documents that were rejected. So using those documents, we can format our training data in the format you see there, which is __ state __ space, followed by the document 1 per line. If you're familiar with some of these tools, that format probably looks really familiar. And that's because you'll see later that a lot of tools use that format. So that's our training data, all combined. So the document classifier that we're building was trained using Facebook's fastText library. And so what we did is we divided the data set that you saw a little snippet of there in that past slide into 80-20 standard train test subsets. The pre-processing steps that were applied, we actually did different combinations to find the ones that were most ideal. These are the ones here that gave us the best performance. For your text, different domains, it might vary. So best to take some best practice, but also remember a little experimentation might be required as well. We removed English stop words, removed tokens consisting of less than 3 characters. In our text, anything less than 3 characters was essentially irrelevant. Lowercase all text and removed all punctuation. After doing that, our classifier trained was able to give us 82% accuracy. We were pretty happy with that. That was, I touched a little bit later on, but without overfitting our model, that seemed to be a pretty good percentage to start with. So if you're not familiar with fastText, it's a open source library from Facebook. One plus of it is it does not require a GPU to operate. Just runs on regular old CPU, does not require many resources, and it's quick. It can train documents relatively quickly. It's a library, as they call it on the site, for efficient learning of word representations and sentence classification. So you can make your word vectors and things in it and do the document classification, which is what we're using it for here. They have available pre-trained English vectors and multilingual vectors that you can download from the fastText site to use in your own applications so that you don't have to retrain them or train them at all for yourself. And also models available for language identification. And below it is the citation for fastText. One reason that we use fastText is its ability to handle out-of-vocabulary words. So in our domain, with the highly technical text, as the documents change over time, so does the text. And so the vocabulary is rapidly changing over time. And so to be able to handle those out-of-vocabulary words is very important to us. So fastText uses character level engrams, which is beneficial for the technical text. So instead of learning on a word like system, systems, or systematic, it works on the character level engrams of each of those words. So later, if it sees a word that looks similar to system in some regard, it will be able to identify it as being somewhat related to system. So in a domain of technical text where component names can change but can be somewhat similar over time, this is really beneficial to us. The out-of-vocabulary words, just an example to help try to illustrate it. Technology, they're broken down into the engram, the character level engrams, left bracket TE, just the beginning of the word, and then each character engram in it till the end of the word. So yes, this is a little different than the original word2vec that we're mostly probably familiar with. And the more recent BERT and ELMO methods of word vectors also operate on character level. So training the classifier, our fastText classifier, we went through many different combinations to find what was most optimal. And this is a summary of the hyperparameters that we had the most luck on. Again, this is probably fairly specific to our domain. So if your documents may be different, so performance may vary, just have to do your experimentation to find out. What we settled on was 100 epochs for the training, word engrams of size 5. And the word engrams are important when word order is important. So if you want to maintain the word order in your source documents, it's important to use those. And we found in our text that word order is important. The words were chosen very carefully. And so maintaining those phrases in that order is important to the classifier success. Learning rate of 0.1. The minimum number of characters, 3, and the max number of characters, 6. So that's how many engram characters you consider at one time. A word has to occur at least 10 times in the text. for it to be considered. If not, it's thrown out. And so this helps find words that are more important than others while filtering out some of the noise. The loss function hierarchical softmax was used. So evaluating the classifier was done through a scripted grid search. Essentially, the hyperparameters for many types of, or many different trainings were defined, and then they were run across multiple systems. And those results were stored in a database. And this just allowed us to be able to come back, look at them later. Again, fastText is pretty quick at running. For our 50-some thousand documents, training just took a few minutes. So we were able to go through these at a pretty quick pace and get good feedback. This is, of course, an iterative process, and grid search is, of course, not typically the best thing to do. fastText does have hyperparameter optimization around F1 score. So when enabled, it will choose random values and try to get the best F1 score for your model. So managing risk. Creating a classifier around the documents brings some risk into the process. And some of that risk is human risk, where we don't want the authors of the documents to think that because they got a bad prediction that their document is bad. That's not the case. The documents change over time. Just because a document got a low prediction for being approved does not necessarily mean the document is bad or it should be abandoned, deleted, thrown in the trash, or anything like that. So that communicated via training and documentation to the authors to make sure that they know. And we don't want a consistently low prediction score to prohibit a document's progress. The documents and terminology in this domain change quickly over time. Kind of like what we heard in the keynote this morning, the model becomes stale. And it has certainly become stale here and must be retrained as new documents become available over time. A prediction is just that, a prediction. It's not intended to the user to be a final determination of any kind. Another piece of risk was model overfitting. Of course, at times we were able to get higher prediction, but the model was clearly overfit. It would not apply to new data at all. So the 82% seemed to be the best combination of training the model without overfitting it. And our measure was recall. These documents could impact human safety, so it's very important that we maximize recall. So that was our document classifier. So we were able to take the documents that we previously had, gone through the workflow, create a classifier on them, and offer a prediction to the document authors when they're creating new documents as to what end state their document will end up in. So step 2 is we now have given the user some type of prediction of their document, but like I said earlier, it's not a lot of help. And so we want to be able to give the authors a little more feedback. So what we did here is we took the documents and wanted to provide some help to the documents, to the authors when writing the documents through auto-suggest. So when we look at these documents, trends are very much stand out in the documents. The use of dictionary words versus non-dictionary words. Documents that end up being approved have much more non-dictionary words than dictionary words. It was just something that stood out to us when analyzing the text, the contents of them in there. The frequency of common phrases. Documents that end up in an approved state have phrases that occur very often in relation to documents that don't end up in an approved state. So we wanted to be able to use aspects like this to be able to improve, offer feedback to the authors. So the auto-suggest, it's just illustration. I know we all know what auto-suggest is here. And I also just wanted to use the cool little turned around brace bracket that looks like a mustache there. So the quick brown fox and then some suggestions there. And then on the right side, rank them. So you think about this in our domain, of course, that's not what the text is, but as they enter some text, it gets back a list of potential completions, suggestions, and then ranks those suggestions based on some factors. So the source documents for training. We have two sets of documents in our training. We have the documents that have previously gone through the workflow in the approved state. And we also have documents that are currently in the submitted state that we predict to be approved. So there's a little bit of risk in bringing those in, but we think they're valuable to use them. And so we do use a configurable threshold value to provide a cutoff. So for example, if a document is currently in a submitted state and our prediction for approved is 40%, we don't want it. So we want a threshold there of 80%, 90%, whatever it might be, so that those documents are considered. Extracting n-grams from the documents. We extract n-grams of lengths 2, bigrams, and trigrams. And yes, I admit this slide is just a way to get a picture of my dog in there. But in case for n-grams, we also collected the n-gram frequencies. And note that for a large set of documents, it can be a very time-consuming process to extract n-grams of sizes even just 2 and 3. So training our learning to rank model. So we extracted our n-grams from the source documents. The prefixes of length 3 are taken from each n-gram and ordered by frequency. And so then we know from ordered list of most occurring to least occurring those n-grams. The prefixes, the suggestions, and the additional attributes, we use those to define our learning to rank features, which I'll list later on. And with that, the model, a learning to rank model is trained. And it is very important that retraining is periodic as more documents become available. So as documents go through the workflow and they are approved in the final state, we bring those documents in, retrain the model to keep it fresh without it getting stale, because the terminology and the language just changes so fast. So using the learning to rank model. So as authors edit their documents, when they type 3 letters after a white space, we use that to provide a list of autocomplete suggestions. What happens here is a call is made to a web service that's hosting the model, and it returns the list of sorted candidate suggestions. So the web service finds a list of matching n-grams, then ranks the n-grams by applying the model, and that list of n-grams is returned. So learning to rank features that we have here. The frequency of the n-gram candidate suggestion. So of course the ones that appear more often is definitely an indicator that might be useful. The edit distance between the prefix and the n-gram candidate. So phrases and words that are more similar to others is important as well. And I mentioned earlier that the documents have metadata values associated with them, and this is where we use those. So keyword extraction per document topic. So the different documents can have different topics about them, so we can use those topics to provide features as well. Lastly, expert spot review from the more seasoned document authors to provide a judge on relevance for some of the terms. It's still a bit of an open question to find the most optimal features, but that's what we have right now. Other features that we considered, such as time-based features and location-based features, such as when a document is created or relation to location, is not relevant for us. It doesn't have any impact on the document flow through the workflow at all. So now that we have our learning to rank model, we can integrate that into the document authoring process. So the integration of prediction, we took our model that we had and we wrapped it with a very simple REST service, very simple. So as documents are being created, they are sent to this web service, and the web service responds with the prediction for each final state. So it simply gives back the 3 final states and a predicted probability for each one. And that score gets passed back to the user through the interface for their feedback. The integration of autosuggest, we use that same REST service and added an endpoint that accepts a prefix in the document. And the service gets a list of the candidate n-grams. From it, it ranks them and then returns the top n subset of those ranked n-grams to the user interface where they're writing the document so that they can be able to have that feedback. The REST API, as I mentioned a little bit ago, very simple. 2 endpoints, one to predict, post the body of the document, and the response is simply the 3 terminal states along with the predicted probabilities. Same for the suggestions, just a get call given the prefix and the list of suggestions. The tools and summary that were used here. The learning to rank was handled by the Java library called JForce. It's up on GitHub, open source. It's an older library, but it implements Lambda Mart, and it's very good and pretty easy to use. In this situation, it was an environment where the choice of tool is fairly limited, but this one fit the bill and met the requirements really nicely. And fastText, which I touched on earlier, for doing the document classification. That bottom link on the fastText site walks you through using fastText for supervised classification, which was essentially what was done here. Summary, so described a document workflow. We created a classifier to predict the final state as a document as it goes through the workflow. We created a phrase autosuggester to help authors improve their documents' chances of getting into the approved state, and then we integrated those into the document authoring process through feedback. Thank you. If you have any questions. Yes.
Questions. One, when you provided the list of suggestions provided by your LTR model, and you got some number, some order from the active user, was that then used as training data to retrain the model?
It's not currently. We have talked about that, but it's not currently used that way. No.
So the other question is, in providing examples to rank with the LTR model, you took it from frequent n-grams from the data set. If you're already doing a fastText-based model, why didn't you just build a language model? Just do predictions from a language model?
We started with that. We didn't go down that route. I don't remember the reason, but a language model was the first thing that we came to mind. We went this way. I apologize. I don't remember the rationale at the moment. Sure. Yes.
Why did you choose the fastText embedding over, say, BERT and the other ones?
This work was actually done before BERT was released. And so one thing that I would love to do in future work is to apply BERT to it and perhaps fine-tune BERT on the documents now and see and compare how the performance is. Yeah. Yes?
So in systems like these, when classifier is the first step, class imbalance becomes a problem. So for instance, if users are using the system and now more documents are getting accepted all the time, you can come to a situation where your data set for classification is heavily imbalanced by the accepted class versus the non-accepted classes. So, which would mean that you can't retrain your models, or do you have to do something? So have you
we have not. We may be lucky here, but our number of approved documents is very small. So the most documents that go through the workflow don't end up as approved. So we are.
Actually, I asked because we had a similar not yet approved, I will make changes.
Yes.
And the class imbalance basically became such a big problem that we couldn't have a trust in the classifier.
Gotcha. Yeah. Any others? Yes.
Do you know what kinds of things were behind the model that was making it the most significant factor between approved and not approved?
No, not really. Intuitively, the use of technical terms. So it's a human that makes a decision, the final state that it moves to. And intuitively, it looks like that documents that are lighter on technical terms don't get approved. So the more technical you can be, in regard to whatever it is you're writing about in there, the more technical you can be and the more precise you can be seem to increase the odds. Yeah. Yes?
Yeah, just on the note of class imbalance, I was wondering, you mentioned 82% accuracy on your classifier. Do you have an F1 score for correctly classifying approved documents or?
No, I don't think so. So the 82% was just pure accuracy. To maximize our recall. I don't remember that value, but we wanted to maximize the recall because a lost document could have human safety implications. So we wanted to be on the safe side, and so yeah. Others? Anything else? Yes.
So when you provide feedback to the authors about the probability of it getting accepted, and since this is a neural network, was there like any sort of detailed feedback you could provide them, or just a number?
The number was the first thing, and then after that was the suggestion on the phrase query completion. That's the only thing right now.
But technically, could you provide anything more based on that from that model, or not, if you chose to?
I don't know of anything offhand that we could. Of course, the initial feedback was the 82% is great, but how does it help us? What do we do? And so that was where we went to there. I don't know of anything offhand that we could also provide back. But one thing that we did learn is that the more feedback you can give, the better. Absolutely. Yeah. Yes.
Can you explain a little bit in brief about the auto-suggest model that you built with the aircraft? Like how were you able to rank them were you using the lambda model?
Yeah, so uses a library called JForce on GitHub. It implements LambdaMart, and so you define your feature vectors, and our features were things like popularity, frequency in the document, edit distance between those, as well as document topics. So if you're writing in one topic, and this one is also in that topic, then that's a feature as well. So those features work together to train the model. And so after applying that model, that's what ranks the features that are returned to the user. Yes?
You mentioned that your accuracy levels were about 80%. Were there any baselines that you considered to determine that it is good? And actually, if you go to how exactly you did that accuracy?
Yes, so the 82% accuracy is simply of everything that was returned. So of every 100 documents, excuse me, that was returned, 82% of them were calculated correctly. So 82 out of 100 is how we got that. We did not really have a baseline. Going into it, we didn't know what to expect. Our expectations were actually really low, and we were kind of we were kind of exploration, kind of an experiment. And we started out the first run on using this. We had got about 50%. Even 50% was kind of exciting for me and them because it showed promise. And so then once we kept going through the grid search, we were able to get up to about 82% without too much fear of overfitting. We all were pretty happy and pretty thrilled with that. So we didn't really have a baseline or anything that we were shooting for. It was more of just, we think this will be helpful. Let's go from here and see what happens. Others? Well, thank you all very much.